Alright, so today I'm gonna be explaining this important article with the title Memory-Based Message Passing, Decoupling Message for Propagation from Discrimination. So this paper in 2022. Message passing is a fundamental procedure for graph neural network in the field of graph representation learning. Based on the homophilia assumption, the current message passing always aggregates features of connected nodes, such as graph Laplacian smoothing process. However, real-world graphs tend to be noisy or non-smooth. The homophilia assumption does not always hold, leading to suboptimal results. A revised message passing method needs to maintain each node's discriminative ability when aggregating the message from neighbors. To this end, we propose a memory-based message passing method to decouple the message of each node into a self-embedding part for discrimination and a memory part for propagation. Discrimination and propagation. So we develop a control mechanism and a decoupling regularization to control the ratio of absorbing and excluding message in the memory of each node. So our MMP is a general skill that can work as an additional layer to help improve traditional GNN performance. Recently, the emerging graph neural networks have demonstrated powerful abilities in semi-supervised classification tasks. But the message passing mechanism underlies the assumption of local homophilia. That it means connected nodes tend to be the same class. It can be seen as a Laplacian smoothing progress, which smooths each node's embedding by neighbors. Although the local homophilia assumption seems reasonable and helpful to achieve good prediction results for homophilous graphs such as citation network, it also limits GNN's applications in heterophilous graphs. Heterophilous graphs widely exist in real-world society. For instance, nodes in actor networks with diverse roles are more likely to be connected, and different amino acid types tend to form connections in protein structures. In such heterophilous graphs, the performance of classical message passing graph neural networks, such as GCN, graph attention, is even inferior to a simple multi-layer perceptron. What a shame. The reason for such degradation is due to massive presence of different labels for connected nodes in the heterophilous graph. To this end, we propose a novel memory-based message passing mechanism which decouples the messages into two parts: memory for propagation and self-embedding for discrimination. Specifically, each node is endowed with a memory cell and sends messages from the memory cell instead of hidden self-embedding. After propagation, each node can leverage a learnable control mechanism to adaptive update its self-embedding and memory cell according to their recent states. A decoupling regularization is also applied to enhance the disentanglement for the feature propagation and discrimination. Given labels of the nodes, the task of semi-supervised node classification is to predict the labels of the unlabeled nodes. The general message passing is composed of an aggregate step and an update step. Each node first aggregates information from its neighbors, then update its self-embedding as follows. So for the elf layer of GCN, we use H sub I to represent the embedding of node I. And but for the update, we apply a control mechanism, this f theta, to calculate the coefficients alphas to the ratio of absorbing the message and the ratio of discarding the message. The function f theta is said to be a shear-weight, fully connected linear layer with a sigmoid function, so that all the coefficients are ranging from 0 to 1. So we have sigmoid, so we can do this kind of thing easily. So we also know that the current recurrent model like GRU can also be utilized to implement the f theta, which we leave for future work. Compared with vectorized coefficient for controlling each dimension, these scalars alphas can simplify the optimization process and prevent overfitting. So, when updating the hidden state, we linearly combine previous hidden states and the aggregation message according to coefficients alpha. Such an operator may help each node maintain the discriminative ability and aggregate messages adaptively. For instance, when the message from other clause is inconsistent, so it's all about learning, you see. There is nothing about kernels, no local structural things. So it's all about, it wants to learn everything. I mean, the amount of learning is huge. That's why it has lots of local minima. So, but in reality, we need inductive bias so that we reduce the number of these local minima to reduce it. Otherwise, we have lots of local minima, and the problem becomes totally from the perspective of learning, not from the perspective of topological things on random walks. And because random walk, both the traditional and the anonymous random walk provide some insight into the local structures. And when you combine the kernel methods, it becomes so powerful. So let's carry on with this article. The key idea is to decouple the feature for message passing and discrimination of each node. But the idea is very beautiful. Since we use additive model to mixture the embedding, this memory cell and hidden state may be intertwined to increase the difficulty of the decoupling. Inspired by ensemble learning that encourages the base learner to be diverse and independent to achieve better predictions, we adopted decoupling regularization term to enhance the disentanglement between the memory cell and the hidden state. The overall memory decoupling regularization is like this. So, defining the decoupling loss with the cosine similarity, our approach encourages the increment of memory and hidden to be orthogonal. So we add the decoupling loss with the semi-supervised and then the final loss. But C and H are very important. This C is M and M alpha. So the reason that we calculate this C is because it goes directly to the decouple and then backpropagate, of course after adding then backpropagate to correct their learning parameters. So they just get a sense of M and alpha C, and that's it. And then they use this cosine similarity to get a sense of closeness of them. So it's all about learning, and It's not about anything else, not topology, not local structures, not global topology, not local structural things. But they have some good results. For example, in PubMed, 90%. Oh, of course, that is not the hours. The hours is this one. 80. For Quora is 88. For Quora is 88. And the test accuracy, plus minus the standard deviation, you can see for Quora and sites here that if you add edges, the accuracy drops. If you add edges, the percent of edges.